Okay, moving on to de Moivre's theorem. De Moivre. Okay, this is a theorem that helps us deal with powers of complex numbers. Okay, and primarily what we'll be using, the form that we'll be using this theorem in is we'll be using polar form. Okay, so polar form is really nice because it helps us find powers of complex numbers. If we can get those complex numbers in polar form like this, then we can find the powers of these numbers. Okay, here's an example. If I take z, which is the magnitude of z, cis theta, and I square it, I end up with z cis theta times the magnitude of z cis theta. And the magnitudes come together, and the cis thetas come together, and we can add these two angles together, right, from the properties of cis, okay? And we end up with z magnitude squared times cis of 2 theta. Same thing with z to the power of 3. Well, z to the power of 3, or sorry, z cis theta to the power of 3 is the same as having this times this times this, right? And I can replace these two with just the squared term that we found up here, and then multiply it again by z cis theta, magnitude of z cis theta. Okay, and we end up with z, magnitude of z, cubed, magnitude of z cubed cis of 3 theta, because now I'm adding these two numbers, okay? So in general, what we can do is we can generalize this, and as we keep raising this to the power of n, you'll notice here that this n, okay, this becomes this number, and this number also becomes this number, okay? So we have this formula here. This is de Moivre's theorem, and this says that if I raise a complex number that's in polar form to the power of n, then I can take the magnitude of my original number, raise it to the power of n, multiply it by cis of the original angle times n, okay? And this is true for all rational numbers n, okay? Not rational numbers of n where n is an element of Q, okay? All right, so let's try a couple examples here. Find the exact value of root 3 plus I raised to the power of 8 using de Moivre's theorem. Okay, what did we say about using de Moivre's theorem? It's very useful to get our numbers in polar form. So if I can just get my complex number here in polar form, I can use de Moivre's theorem. So how do I do that? Well, let's figure out what root 3 plus I would be in polar form. Okay, so this is a real number, this is a complex number. If we draw it, we would see that we're going to have positive. This would be over positive root 3 and then up 1. So that's root 3, 1. This is going to be a 30, 60, 90 triangle. Okay, this angle here, since it's opposite 1, would be pi over 6. So this would be 2 cis of pi over 6. Okay, now now that I have this form here, then root 3 plus I raised to the 8th power is going to be, okay, 2 cis of pi over 6 raised to the 8th power. And now we can apply de Moivre's theorem, and de Moivre's theorem says, well, take the magnitude of the inside, raise it to the power of 8, times the cis of this angle times 8. Okay? And so this becomes now, this becomes 2 to the power of 8. Cis of, that cancels, so that would be 3 and that would be 4. So it would be 4 pi over 3, right? And where is 4 pi over 3? Now, you could do this a couple ways. You could write this out into Cartesian form and then do that, or you could just use yeah, actually let's use that method. Whoops. I'm going to use this complex, use the unit circle here. So 4 pi over 3, that would be way over here, right about there. Well, that looks more like a 45. How about right there? Okay, that would be 4 pi over 3. And it would be 30, 60, 90 again. Okay. So this, if this was 1, okay, since I don't want to deal with this 2 to the 8th power, let's just deal with this in the unit circle. This would be 1, and then this would be minus 1/2, right? And this would be, since this is 60, and this would be root 3 over 2 minus. Okay? And so we would have 2 to the 8th power times minus 1/2 minus root 3 over 2i. Okay? And if I do this, I'd get minus 128 minus 128 root 3i. Okay? And so this would be the exact value of this raised to the power of 8. All right? Let's try one more. By considering the cosine of 2 theta, okay? By considering the cosine of 2 theta plus I sine of 2 theta, how can I use this to show that cosine of 2 theta and sine of 2 theta are the double angle formulas that I'm familiar with? Okay, so let's think. What is cosine of 2 theta? Okay, cosine of 2 theta is cosine squared theta minus sine squared theta, or the variations of this, which would be, if I replace this as 1 minus 2, or 1 minus sine squared, that would be 1 minus 2 sine squared theta. Or if I replace this with 1 minus cosine squared, that would be 2 cosine squared theta minus 1. Okay? And so okay, so then this becomes sine of 2 theta is also 2 sine theta cos theta, right? Okay, so I want to be able to find this one here or this one here. Okay, I need to somehow find that these can be deduced using this. Okay, so let's think, how am I going to do this? The cosine of 2 theta, let's just start from the top. Cosine of 2 theta plus I sine of 2 theta is what I have. Okay, now what can I do here? Well, if I write this in polar form, I end up with cis of 2 theta, right? And cis of 2 theta, by using de Moivre's theorem, is actually the same as cis of theta. Since I need to get somehow cosines of theta and sines of theta, let's use de Moivre's theorem and get rid of this 2 theta here. Okay, so now this becomes actually that, right? Because that's 1, that's a magnitude of 1. Okay, and this is by using de Moivre's theorem. Okay, so how does that help me? Well, now if I expand this out, cosine of theta plus I sine of theta, okay, and then I square that. Now I have a, if I were to do FOIL here, okay, if I were to do FOIL, I would get cosine theta plus I sine of theta times cosine of theta plus I sine of theta. Okay, and if I do this, then I'd get cosine squared theta plus 2I sine theta cos theta, okay, plus I squared sine squared theta. Okay, well, what's this? That's just negative 1, right? That's negative 1. So this becomes cosine, let's group these properly. So I end up with cosine squared theta minus sine squared theta, okay, that looks pretty familiar, plus 2 sine theta cos theta times I. And that also looks very familiar. Okay, so here I've found the cosine of 2 theta, and here I found the sine of 2 theta. And this is basically the same as cosine of 2 theta, and this is the same as sine of 2 theta, so we can say these are the double angle formulas that we're interested in. Okay?